Here we're going to look a little closer at tangents of circles. You saw that in the beginning circles lesson. You'll see some terms we've seen before, and we'll just go over them again. There's a lot of examples in this, so we'll split this up into a few parts. So you will be able to use the Pythagorean theorem to find lengths of lines and/or line segments that are tangents to a circle. We'll see a couple of special properties about tangents and circles. So first, some terms. We've seen this term before. A chord is a segment whose endpoints are on the circle. So it is a segment. And of course, the diameter is the longest chord. So here's a little sketch, of two chords. Here's the diameter, the longest chord, just a segment, not a line. Same here. Here's a chord right here where the two endpoints are on the circle. Now, a secant is a line or a ray that intersects a circle at 2 points. So it's similar to a chord, but a chord is a segment, whereas a secant is a line or a ray that touches the circle at 2 points. Tangent, we've seen before, is a line, a segment, or a ray that intersects the circle in exactly 1 point. So here's a picture of a segment, or you can put arrows on it, right? It just intersects at 1 point. We're going to see some special properties about tangents in this lesson. And then, of course, the point of tangency is the intersection of the tangent line and the circumference of the circle. The 1 point there, that is the tangent, point of tangency there. Remember, if I go too fast, you can pause it. It's best to listen to it and see the examples and then pause it and go ahead and copy the things down. Listen to what's going on, the reasoning in some of these problems that are going on, and then pause it and copy down the information is the best way. So here's just another little word bank. We're going to look at these things. Let's see, a chord. Oh yeah, that's this thing right here, a segment that intersects at 2 points. Point of tangency. Oh, there's the tangent line right there. So the point of tangency is that point T right there. A secant line is the line that touches the circle at 2 points. So there's the line, not a segment. So our secant is this line EA. And then, of course, our tangent line was right here where it touched the circle at 1 point. No big deal there, just reminding you of these terms. So here, a little more terms. The center of the circle, of course, is this point A. They want all the radii. A radii goes from the center to a point on the circle. So AB is a radii. AE is a radii. And what? AC. There's 3 of them in there. Goes from the center to a point on the circle. And they're all the same size. That's what a circle is. Distance is the same all the way around it. So any radius is equal. If this radius was 5, so would these other 2. So we look at all chords. A chord is a segment. So I can look at this segment right here. Segment ED is a chord. Even though there's a line drawn there, you can talk about the chord that just goes from E to D and put the little segment symbol above it. Also, there was EB. That was the biggest chord, the diameter. And the other one was ED. Secant is a line that touches the circle at 2 points. So this whole line here, so we put the line symbol above it with the arrows on the end. Line ED. A diameter is a chord that goes through the center all the way across there. So that diameter is EB. Remember, the diameter is 2 times the radius. The tangent line was this line right here. I'm going to call it FH, I believe. And the point of tangency is that point where it does the tangent line does touch the circle. That was point G. So later you'll do the quick checks. I'll get those online for you and answer these questions. I think I'm going to do one big quick check with all the quick checks in the whole thing. Now here's our first property of these tangent lines. It says if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So perpendicular means it intersects at a right angle, a 90-degree angle. So here's my picture. Okay, here's my tangent line, and it is perpendicular to the radius. Here's the radius drawn. So what we get here is a right angle here, a 90-degree angle. And you'll see we'll be making right triangles in problems by taking this radius to this point out here somewhere and using Pythagorean's theorem to solve for some things. But the biggie to remember is that when you have a tangent, it's going to make a 90-degree angle with this radius that goes to the point of tangency here. There'll be 90 degrees there. So let's look at an example how we use this property. I want to do example 2 second. I'm going to go ahead and do one of the quick checks for you just because it's a little more easier, and then we'll come back to this problem. Okay, so go to the quick check right after it. This one right here is a little better one to start with. Alright, so here is that property. This is a tangent segment here. It touches the circle at one point, and this is the radius. So that's where we draw in our 90-degree angle. So I'm going to put that in there, put that little square there. This is 90 degrees. So now, to solve for this whole side over here, this is part of this right triangle. We're going to use Pythagorean's theorem, which says take the leg and square it, take the other leg and square it, it'll equal the hypotenuse squared. So these two sides over here, the two legs are the two sides that make up this right angle. This one and this one in red. This other side is the hypotenuse. So these are the two that go over here. It doesn't matter which one you put, the order you put them in, but these two go over here, and this hypotenuse side, which is x in this problem, goes over here. And they're all raised to the second power. So it looks like this. One of the legs is 15, so 15 to the second power. The other one is 20, so 20 to the second, plus 20 to the second power, equals the hypotenuse to the second. The hypotenuse is what we're looking for. We're calling it x right now, so x squared. So this is pretty easy to solve. You're going to put this into your calculator. If you put in 15 squared plus 20 squared, and you should do this right now, you know, or at some time, make sure you get these same answers as me. So 15 squared plus 20 squared is 625. Of course, equals this other side, still x squared. To cancel out the square and get x, you have to take the square root of it. It looks like this. And all that does is cancel out the power and leave us with x here in a minute. So we have to do the same thing to the other side, take the square root of it. And the square root of 625 is exactly 25. So this x, this side we were listening, the hypotenuse there is 25. It's that simple. We'll go ahead back to that example before this and do it and see how it's a little bit tougher, but not too bad. So again, the first thing you're looking for, we've got this right triangle here. Why is it a right triangle? Because this tangent segment here and the radius make the right angle. You know, the first thing I do is draw that in. Okay, there's my 90-degree angle. That way I know which ones are the legs. The two sides that make up this angle are the legs, right? So this whole side is the hypotenuse. Well, they don't want the whole side. They want just this little piece. But I'm going to solve for this whole piece, whole side over here, and then subtract this piece, which is a radius. Of course, this is a radius, so this radius is the same. This is 5. So I'm going to call this whole piece over here y, since we've already used x. You know, this whole side is going to be y. So I know if I figure out what y is and take away this 5 radius, I'll get what's left, x. You know, basically like this. This is what we're gearing up for. Whoops, I kind of showed you the answer there. Oh, no, I didn't. The x piece will equal the whole thing minus that little radius piece. So I'll take this whole side, which I'm calling y, subtract away this radius, and I'll be left with x. So the first thing is to solve for this whole side we're calling y right now, using Pythagorean's theorem. So here are the legs. So we're going to take those and square those and add them. And it'll equal this hypotenuse, which we're calling y right now, the whole side, squared. So there it is. We put those two things in there in our calculator. 5 squared plus 12 squared equals 169. Then, of course, to get rid of that power, we got to take the square root. And we end up with y, that hypotenuse, that whole side, equals 13. So now we know the x piece will equal the y, the whole thing, 13 minus that little radius will leave us with this x, and that equals 8. So it's a little different than the other one. We're just solving for a piece of it. Some other problem we may be solving for the radius or something. Alrighty, I'm going to stop this video now because it's getting a little long, and we'll do another part in a minute.